Okay, this section is going to discuss about the transformation method for the continuous random variables univariate case. Only one variable, okay, univariate case. So here's the theorem. So we are going to consider a random variable x. Now this is a continuous random variable. Okay, x is a continuous random variable. RV stands for random variable. And I will usually use C and TS, the short form for continuous, okay? And our PDF is fxx, you know the notation, and it is greater than 0 for all x. That should be the condition satisfied for PDF. These are probabilities, they should be greater than 0, okay? And we are going to define the new random variable y. Let's say it's a function of x, which is hx, right? Can be gx, any letter can be used here. Okay, just a function of x, say hx. And we are going to assume that h is differentiable and strictly monotonic. It's differentiable and strictly monotonic. Why we assume that is, okay, you can see it from the equation that you have dx over dy, a component there in your fy. Okay, that means it should be differentiable and it is strictly monotonic. What is the meaning of strictly monotonic? That means it's either increasing or either decreasing. Okay, either it is increasing or either it is decreasing, not both. So it's strictly monotonic. And I'll explain why we again use that monotonic definition or the condition. Then for that, the new variable y, the PDF of y, which is hx, okay, it will be fxx multiplied by the determinant of dx over dy, or the absolute value of dx over dy. Okay, since this is the univariate case, your determinant will be just one value. So it is going to be the absolute value. And we know that you can write x as the inverse function. Okay, that is the inverse function h inverse y. Okay, so your fyy will be the density function of fx evaluated at this inverse function h inverse 1y. So that means wherever you see the random variable x, you replace it with the inverse function. That means you will end up with the function of y. Okay, h inverse y is a function of y, right? And then you multiply by the determinant dx over dy, again x will be replaced with h inverse y. Okay, now although it seems like a little bit complicated, but when you do the examples, you will see that this is very simple, and when you understand it, it's actually very easy. Okay, if you can find the inverse function of this h inverse y, you know how to do that. Okay, changing the variables x to y and y to x, you get the inverse function and simply replace it with the PDF of x. fx will be given to you. Replace x with the inverse function, so you'll end up with the your function of y, and then multiply it by the first derivative and its absolute value. Okay, so let's get the proof of this and see why we end up with this absolute value and everything. Okay, and why we consider this monotonic property and everything. Okay, right. Now recall that the theorem, it says fx is greater than 0. Okay, if it is always greater than 0, fx, and it is strictly monotonic, either increasing or decreasing. That means we are going to do the proof for both cases. We have to consider the increasing case and also decreasing case. Okay, and we assume that h is differentiable, right? So keeping those things in mind, let's do the proof. Okay, so pay attention very carefully. I will be uploading the notes so you can refer it. So look at this proof. Right? So we are going to consider this in two cases. Let me change the size. Okay. So case one is, we are going to assume that our function h, what is this function h? That is the function of x. Okay, it can be a linear function, quadratic function, okay, whatever. Anyway, it should be monotonic. Okay, this is a monotonically. The first case is when it is increasing, monotonically increasing. The second case, we look at monotonically decreasing functions. Okay, so if it is a monotonically increasing function, right? So let's see, what does that mean? So y equals hx. So when we assume that h is monotonically increasing, what is the meaning of that? So let's draw the graph. Here's our x-axis, y-axis, right? When you have our function h, okay, monotonically increasing, that means it's always going up. Okay, it's always going up. Okay, and if you think about the points, let's take 2 points, x1 and x2, right? When you find the y, the corresponding y of x1, okay, so that means our y will be h of x1. Okay, so this is our y1. Y1 is h of, so this is our hx. So x1 will be the corresponding point for y at this point. Okay, if you take the coordinates for x1, corresponding the y value will be hx1. And then in the same manner for the second point x2, our y2 will be h of x2, right? So by increasing we means hx1 is always less than when hx2 when x1 is less than x2. Okay, so that means when x1 is less than x2, that means it is the order x1 and then comes x2. If it is increasing, the hx1 and hx2 will also have the same order. Okay, so if x1 is less than x2, you can see that y1 is also less than y2, which is hx1 and hx2. So that is the meaning of increasing. Okay, now let's look at the CDF of this function, right? You know the definition, capital Fyy, this will be, according to the definition, the probability, the capital Y less than or equal any value y. But what is our y? That is our function hx less than or equal to y. And if we take the inverse, this will be simply x less than or equal h inverse y. Okay, when it is increasing, you get the same sign. Okay, you get the same sign. So if you take the inverse, okay, because when x1 is less than x2, y1 is also less than y2. So when hx is less than y, the inverse, okay, so this is the, because x1 is the inverse is h inverse xy, x1, h inverse x2. Okay, so likewise, therefore, the same, the inequality will hold because it is increasing. Okay, and what is this? What does that mean? What does the probability x less than or equal h inverse y means? This is again the definition of the CDF, which means now instead of y you have x, so that this becomes fx at what? H inverse y. Now you can see how this h inverse y comes here, right? It is from this the CDF. Okay, is this clear to all of you? These two lines. The CDF of y, according to the definition, is probability y less than or equal to simple y, but capital Y is hx. So you have less than or equal to y. Because this is monotonically increasing, it is always increasing, and in the same ratio. Therefore, the inequality will hold when you take the inverse. Okay, so when you take the inverse, you have x less than or equal to h inverse y. And if you look at this formation, x less than or equal, so that is the definition, the probability x less than or equal some number, that means it is the CDF of, now the variable is x. So you have fx at h inverse y. Okay, so you have the CDF of y, but what we want is the PDF of y. So how do you get the PDF? You have to get the derivative. Okay, so let's take the derivative of this function, then you'll end up with the PDF of y. So that will be simple fyy or lowercase yy. You have to take the first derivative with respect to y of this function. Okay, so you have to get the first derivative of this function. Okay, now you have to be very careful when you take the first derivative. Now this is the chain rule. Okay, you have to apply the chain rule. Why? You have something inside fx also. So you get the derivative of the outside function, then you go inside and take the derivative of the inside function. Okay. So if you have the CDF capital Fx, the first derivative will give you the PDF. So you have Fx of this same function, right? And then the chain rule, you go inside the function and get the derivative of this H inverse y. So you have, this is the chain rule, dy of H inverse y. So this will be the first case, the PDF of y. Okay, so this is the PDF when y is, or when the function h is increasing. Okay, so we'll leave this for a while and look at the second case. Then let's come back and combine them together to get the final result of the theorem. Is it clear up to this point? Do you have any questions? Anything do you want me to repeat? So please pay attention, okay? Pay attention and understand this. Right? Okay, so that's the case one when h is increasing. Now we move on to the second case. So that will be when our function h monotonically decreasing. Right? So let's draw the graph again. Now, how will it look like? You already know the graph of increasing function. Now you can assume what will happen to the decreasing function. And why are we using this, the first quadrant only? Why are we not going to the other places? Because it says our fx is greater than 0. Function is always in the positive side. Okay. You can have it in this side also, right? Anyway, when we do examples, we'll look at that, right? Now, what will happen to the function now when it is decreasing? It will go like this, right? It will go like this. Now, what will happen to our x1 and x2 and their inverse? Let's see. So here's my x1 and here's my x2. The corresponding y coordinate of x1. Now, where you will get this to be hx1 and this will be y2 or hx2. Now, what has happened? When x1 is less than x2, what will happen to y1 and y2? The inequality is now changed the other way around, right? So you can note it down. By decreasing, we means hx1 is less than hx2. When will that happen? X1 is less than, I'll choose the other way around so it will be easy for you. Let's do when x1 is less than x2. Now you see the sign, it is now different, right? In the increasing case, you have the same direction, but when it comes to the decreasing functions, you end up with the sign change. Okay, so you can clearly see that from the graph. When you have x1 is less than x2, but the corresponding y value y1 is greater than y2. So you see that the inequality will change, right? Okay. Now, keeping that in mind, let's try to do the same thing. The CDF of y. You can see the pattern now. It's very similar to the previous one. Only one change considering this inequality, the sign. Okay, so let's see how that will apply. See, this is the definition of the CDF. And that will be, as usual, y is hx less than or equal to y. Now, what will happen? When hx is less than y, because of the decreasing pattern, when you get x and h inverse y, what will happen now? The sign will change. Okay, the sign will change. Why? Because it is decreasing, and we saw what happens when you get hx and x. The relationship is now the other way around. So this sign will become now greater than. Okay. Now, if you go back to that previous proof, we have to write the CDF, capital Fx somehow. That is the way to get the PDF of y. So you can get the first derivative and get the PDF of y. So you have to write your Fy in a form of the CDF of x. Okay, now if you look at this definition, it is the greater than, but the CDF is always the less than. So what should we do in order to make this less than, x less than h inverse y? How do you convert this to the less than sign? What should you do? Then only we can write it as fx. So if you change x greater than to less than, how do you modify this probability? Yes, you do 1 minus px, exactly. So thanks, Janet. So that is what you do. You have to do 1 minus the probability x less than or equal h inverse y. Right. So these are the basics, the basic probability axioms. Okay, you have learned in the previous courses. So that will be applicable in many places. The definition of the CDF, the definitions of the expectation, the conditions of CDF, the conditions of PDF, the total equals to 1, and the complements like this. Okay, so these are you're going to apply these things every time that you use, or you refer a probability course, or stat course. So those basics that you learn in previous courses, they are going to be used repeatedly, okay, almost all the time. Therefore, you can't forget what you have learned in previous semesters. Okay, even the ST101 things that you have learned in 101, you are going to use them throughout your whole the course, okay, up to the final year. So this is the complement, right? If you have x greater than, if you want to convert it to less than, simply you can take the complement. Okay, so let's write the CDF. Now this is the CDF of x evaluated at h inverse y. Now you can see why we get the negative sign, and if you follow these steps carefully, now you can assume where we got that absolute value, right? So we'll see. Now you have your CDF of y, capital Fy, which is 1 minus CDF of x evaluated at h inverse y. Then let's take the PDF. The PDF of y is the first derivative of the above function. So you get d over dy fyy. What is our fyy now? That is 1 minus fx h inverse y. Okay. Now let's take the derivative. The derivative of a constant 1, this is 0. So you have nothing from the first part, and then you have this minus sign. And then the derivative of capital Fx will be simple Fx evaluated at h inverse y. Then you do the chain rule, the derivative of the inside function. So that will be d over dy h inverse y. Okay. So this will be the second outcome. Now you have two possibilities for Fy. When the function is increasing, you have the first result. When the function is decreasing, you have the second results. Now, if you compare the first and the second results, right, the difference is just a sign, a minus sign. Okay, one minus sign, that is the difference. Okay, now where are we going to include it? Okay, so that's the next, and that's the next question. This minus sign, okay, is in front of the product of two functions. Right, this minus sign is in front of the product of, this is the first function, and the next function is the derivative function. Now, where are we going to incorporate this negative sign? So if you think about the first one, this is actually the positive. positive part and the negative part. Where are we going to include that sign? Is it to be included with fx function or with the derivative function? What do you think and why? Now, what is fx? I'll give you a hint. What is fx? It is a density function. What are the properties of the density function? Those are probabilities. Can probabilities be negative? Can you have negative probabilities? Yes, you can't have negative probabilities. Okay, probability value is always in between 0 and 1. Never exceeds 1, never negative. And fx is a probability density function, so you cannot have a negative value for fx. Therefore, this negative value, the negative sign is associated with the d over dy. Okay, and the same manner, it doesn't matter with the positive, but this will also be gone with d over dy because anyway fx is positive. Okay, now that means we can combine 1 and 2 by considering both the positive and the negative of d over dy. And that is how you incorporate the absolute value. So when you incorporate absolute value of d over dy, that can be the positive or negative value, right? So the reason is fx is greater than 0. This is greater than 0. Why? Because it's a probability density function. It cannot be negative. Therefore, d over dy h inverse y, that is going to be the negative value for this, the second outcome. So this negative value is actually with the d over dy. Therefore, you can combine 1 and 2. So when either the function is increasing or decreasing, depending on the sign, you can write fy y to be the absolute value of d over dy h inverse y. So why this absolute value? So that will incorporate both positive and the negative value. When the function is increasing, you'll end up with the positive. When the function is decreasing, you'll end up with a negative derivative. Okay, it's the slope. It should be negative, right? So that is how you do the proof of the theorem. Okay. So is this clear to all of you? All two cases and then combine it. Now you may have a problem. What will happen if our function hx is both increasing at some place and decreasing at some place? Now in such situation, how do you apply this theorem? Because the theorem says it is strictly monotonic, either increasing, either decreasing. What if your hx is increasing at a certain place and decreasing at a certain interval? Now in such situation, how do you apply this theorem? What do you think? Any suggestions? We'll do an example, but I would like to see whether you can come up with a suggestion. If your function is increasing at a certain interval and decreasing in another interval, how do you handle it? Yes, exactly. That's the answer. You can break it into intervals. You break your support into intervals so that each interval contains either increasing or decreasing. Right? Maybe you have to divide it into many intervals and you solve and apply the theorem for each interval separately and then you combine it. So I'll show you how we can do that in an example. Okay, so exactly that's what we are going to do. Right. Okay, so here's our first example. The PDF of x is given 1 over 2 times x. The support of x is from 0 to 2 and 0 otherwise. You have to find the PDF of y. The first one is when the function is 6x minus 3. That is a straight line, a linear function. And the second one, gx, is 1 over x. Okay, so the 1 over x, it's So we'll look at the function, okay, one by one. Okay, so let's start with the first one. Hx equals 6x minus 3. So why don't you all take a piece of paper and try this with me? We'll do it together, okay? The first thing you have to do is, it's easy if you draw it, this one. Okay, when you have the graph, it's very easy to see the solution. Okay, so let's draw the graph. 6x minus 3, very easy, just a straight line of y equals mx plus y type, right? Okay, so again, can you guess how it will look like? The slope is 6, it is positive, so it is increasing. And the y-intercept is -3. That means the graph should cross the y-axis at -3. That should be an increasing function. Right? You can find the points that it crosses. Right? So here's the y-intercept. And what will be the x-intercept? When y is 0, what is the value of x? Substitute the value and check it. When y is 0, so what is x? Yes. Yes, Siri, thanks. It will be 1/2. So you can easily find that. 3 to the other side, 3 divided by 6. Yes, Julian, you got, okay, so you got the answer. X will be 1/2. So here's our x-intercept, right? And what is the support of x? X is in between 0 to 2. So it will be from 0 to 2. So let's find, yes, it will only be this function, right? This is the area. So what will be the y value when x is 2? When x is 2, what is the corresponding y value? Yes, you need it to find the support of y. That will be 9. Yes. So you have x equals 2 times 6 is 12 minus 3 it's 9. Right. So when x is, the support of x is from 0 to 2. So that this gives us the support of y will be from -3 to 9. Right. So you need this when you write the final answer. Y is from -3 up to 9. Now what do you now look at this function 6x minus 3. Is it oh yeah, sorry. So this should be half 0. Thanks. Okay, now it's correct. So tell me, what is this function? Increasing or decreasing? Is it monotonically increasing throughout the whole interval? Do we have all the conditions satisfied to apply the theorem? Right. So x is from 0 to 2. We found the y, and it is always increasing within the support 0 to 2. Okay, so we can apply the theorem. Okay, so the function, what is our function? Hx equals 6x minus 3 is always an increasing function for all x. What is our x? When you say all x, it is the support of x. Okay, support of x. Right. Now, if you want to find the support of y, even without drawing the graph, you can find it. Okay, why? Because if x is in between 0 and 2, what is in terms of y, right? So, okay, I'll come to that later when you find the inverse function, right? So x, let's find the inverse function. Can you find the inverse function if I'll write it in two separate lines. So if y equals 6x minus 3, what will be x? X will be y plus 3 over 6. So when you replace the values with the inverse, right? So you can write this as the h inverse y, right? So therefore, x is y plus 3 over 6. That means y plus 3 over 6 is in between 0 and 2. So you have 6 times 0 is 0. And when you take y to the other 3 to the other side, you get negative 3 less than equal y. 6 times 2 is 12 plus 3. 6 times 12 minus 3, you get 9. So you get the same limit both from the graph and also from the inverse function. Okay. So you have the inverse function of y. H inverse y is y plus 3 over 6. Right. So let's apply this to our theorem. Very simple. Fy y will be fx, evaluate at h inverse y, absolute value of d over dy h inverse y. Okay. So let's go back to fx. What is our fx? 1 over 2 times x. So what should we do? Now we have to evaluate x at h inverse y. What is h inverse y? Y plus 3 over 6. So what does that mean? For all the places where we see x, we have to replace x with this h inverse y. So where do we see x? We have x at only one place. So let's replace it with y plus 3 over 6. So how do we write it? You have 1 over 2 instead of x. You write h inverse y, which is y plus 3 over 6. So the first part is done. Fx h inverse y is done. Then we have to do the derivative d over dy of what? H inverse y. What is h inverse y? Y plus 3 over 6. Right? So let's do the derivative. You can do the simplification along the calculation. This will be 12 y plus 3. And can you find the derivative of y plus 3 over 6? 6 is a constant, so you can take it outside. The derivative of y plus 3 is a constant, d over dy is 1, so you just end up with 1. Okay, so that will be y plus 3 divided by 72. 12 times 6 is 72. So this is the PDF of Fy. Okay, is this clear to all of you? If this is confusing, you can keep 6 here, right? And then finally multiply it. Since this is increasing, you'll end up with a positive value inside the absolute value, so it doesn't matter. So it's just multiplying by 1 over 6. Now let's write down the final answer in the proper way. This is very important. You can't just stop at here, okay? If it is a PDF, you have to write it in the correct way. And if you want to double check, you can do that also. How do you check whether this is the correct PDF? How do you check whether this is the correct PDF? Yes, how you write the final answer. So you'll get full marks if you do that, okay? So how do you check whether this is a correct PDF? You have to integrate over the support y from -3 to 9, and that should be 1. Okay, so that is how you double check whether you got a correct PDF. Okay. So is this clear to all of you how we applied the function and everything? Right? First you found the inverse function, and based on the inverse function, you can find the support of y, and then straight away you apply it to the theorem. And this is, you can apply it without, proof always. Okay, so this is a proven result. You can always apply this equation and proceed. Okay, so you have to remember this. Actually, it is not hard to memorize, you know, it's just the fx at the inverse and multiply by d over dy. Okay, any question about this one, this example? Is it clear to all of you? Okay, shall we move on to the next one then? What is the next one? Gx is 1 over x. Second one is when y, so now you are using gx. It's okay if you want, you can use hx, just a letter, okay, to mention that it is a function of x. Now, how will this function look like? Again, it is in between 0 and 2, okay? The support of x is still 0 and 2. So how will this function look like? 1 over x. Okay, so here's our function gx. Or you can say y equals 1 over x. So this will be the function of 1 over x. Right, so what will happen when what is the support of x? When x is 2, when x is 2, what will be the value of y? When x is 2, what will be the value of y? Y will be 1 over 2. Yes, so y will be 1 over 2. When x is 0, what will be the value of y? When x is 0, you have 1 over 0. What is that? Will it touch the y-axis? When x goes to 0, y will go to where? Y will go to positive infinity, right? So it will go to infinity. So this is how you have to draw it. It's not touching, so it's going straight up. Okay, so y goes to infinity. So now you can see the support. So y will be from, it will be always greater than infinity, but the lower limit will be 1 over 2. Okay. Right. So let's find the, again, this is decreasing. Always it is decreasing. So monotonically decreasing. We can apply the theorem. Y equals 1 over x. What does that mean? X is 1 over y. So this is our inverse function. So wherever you see x, you have to replace it with 1 over y. That's it. So let's find the PDF. So it's always nice if you write this equation and proceed, even in exams tutorials. So everybody knows what you are using, right? Rather than just writing the answer. So start with the results of the theorem and then proceed. So h inverse x, x is 1 over 2 times x. Instead of x, now we have to write 1 over y. And then the derivative of 1 over y. Right? Can you try this one and tell me what is the derivative of 1 over y? What is the first derivative of 1 over y? So you have negative y to negative. Yes, I know it's hard to write down the type it. So you'll end up with negative 1 over y square, right? Anybody who's not familiar with the derivatives? Anybody from biology stream? I guess you are familiar with these derivatives from your MT100 course, right? So study it if you are not familiar with them, right? And you have the absolute value. So the negative sign, you omit it with the absolute value. So what will be the answer? 1 over 3y, 2y to power 3, right? So that is the answer for the PDF of y. And again, you are not supposed to stop it here. Write down the correct answer. So this will be 1 over y is in between 0 and 2 because 1 over y is x. So if you want, you can write y greater than 1 over 2. And the other side, it is going to infinity. So it should be greater than 1 over 2. 0 otherwise. So this is how you write down the final answer. So you see that when you have a decreasing function, you'll end up with your derivative negative, and with the absolute side at the absolute value, the negative will go away. So you'll end up with the nice PDF for y. Okay, any question about this one? Anything unclear? Right, okay, then shall we move on to the next example? So here's the next one. This familiar uniform distribution, right? So your x is the uniform density in between -1 and 2. You have to find the PDF of y, which is x square, and the support of x is from -1 to 2. So the first thing you have to do is write down fx. Because the function of x is not given, but you know it is the uniform distribution. The uniform distribution within the interval -1 and 2. Right? So you know that if x is uniform distribution, how do you write fx? This is the PDF of the uniform distribution within the interval alpha to beta. Now our alpha is -1, beta is 2. Can you find the function? Right? So what is the function? 1 over 2 minus -1, which is 3. Right? So if you draw the graph, you can clearly see that. Here's our x, y within the interval -1, 1, 2. And the uniform distribution, the probability will be 1 over 3. Okay, the probability is it is 1 over 3 for all the intervals. Right. So this is the distribution of x. But what do we need is the distribution of y. What is y? X square. Now that is the most important thing. You have to look at the function, whether it is increasing or decreasing. Now remember, our function is not this one. Okay, this is just x. Our function is what? X square. The function is now x square. Okay, shall we draw x square also? And see how it will look like. Now these are two different graphs. Okay, the first graph represents the uniform density, and the second graph is the function x, right? So x square, you are very familiar with the graph of x square. It is the parabola, right? In the positive quadrants. So let's draw it from 0, and our limit is up to 2, and this side up to -1. So up to should be symmetric. A nice symmetric function. Okay, but the other dotted area we don't need it because our support is only up to -1. Let me draw it a bit. It goes like that. Now, what is the problem with this function? Now you can find this point when x is 1. So when x is 1, what is y? 1 square, it is also 1, right? So here's our behavior of our function hx. Now, what do you see in this function? Is it strictly monotonic? Is it strictly monotonic? Is it only increasing or only decreasing within the given interval? Yes. What do you see here? It is decreasing in the interval -1 to 0, and it is increasing in the interval 0 to 2. So if you are going to apply the theorem, what you have to do is you have to split this interval into 2 cases. The first one, you can do the decreasing function -1 to 0. Separately, you apply the theorem and find the answer of fy. And then next you do the increasing part, that is within the interval 0 to 2, you apply the theorem again separately. Now it is the increasing function and you find fy. And then you combine these two together and you have to be very careful with the overlaps. Okay, I'll show you how you can incorporate them. Okay, right. So let's start it. We'll start with the -1 to 0 side first. Okay, so shall we write it? The function is decreasing in -1 to 0, and the function is increasing 0 to 2. Right? These are open intervals, continuous cases. Right? Okay, so let's start with the case 1. Sorry. When our x is in the interval -1 to 0, right? That is when the function is decreasing, right? This first case. This is our second case, right? Now, if you see anything unclear, please stop me immediately and okay, ask me to explain, right? So y equals hx, x square. So what is our inverse function? This will be the square root of y. In the decreasing side, and you know, when you take the square root, you always consider positive and negative, right? So any case, if you have, say, when you have to find the square root of 25, you write plus or minus 5, right? Always we consider, because plus 5 square is also 25 and the -5 square is also 25. Therefore, you always consider plus or minus. So here also, when you take the inverse function, you consider plus or minus, and the minus part goes with the decreasing function. That is obvious, right? The decreasing part goes with the negative, the square root part, and the increasing part is going with the positive square root part. So that is how you incorporate this sign, plus or minus, right? Now let's, so here's our inverse function. So let's apply the theorem. Derivative. H inverse y. Right. So our fx is what? 1/3, and you don't see x here, so there's nothing to replace, right? It's a constant, so it is just 1/3. Right? If you see any x component here, you have to replace that x with the square root of y, right? But in this case, our fx is just a constant, 1/3. So that will go here. That's the only thing that comes from fx evaluated at h inverse y. Anyway, it's a constant, 1/3. And then you have to get the first derivative of negative square root of y. Right? So what is the answer? You get 1/3, absolute value of what? Right? You know how to get the derivative of a square root, right? And the negative sign, we'll keep it. So what is the answer? What do you get? I know it's hard to type, so I'll write the answer. To have a negative to square root of y, right? And the negative signs with the absolute value, it will go away and you'll end up with 6 times square root of y. And what is the interval for y in this case? X is in between -1 and 0, right? So let's find that also. Sorry, X is in between -1 and 0. So what will happen to y? Y is, that is the square root of y, right? The square root of y, and it is decreasing. Square root of y will be between 1 and 0, right? So the goes the other way around. So you get 0 and 1. Okay, and you can see it from the graph. This interval 0 to 1. Right? When x is from -1 to 0, y is from 0 to 1. Okay. -1 square becomes 1, 0 is still 0. Right. Okay. Is that clear? So this is when y is in between. Should be y, right? Y is in between 0 and 1, not the square root. Right. Right. Okay, so I have how is the h inverse of y negative square root? Because it is the decreasing part. This is the decreasing function. Okay, we are considering the decreasing part of x square, right? We are in this -1 to 0. We are looking at the decreasing part of the x square function. So when you take the inverse, you get the square root. Always, when you take the square root of any number, you always consider both positive and negative, right? Because I explain it. Because both positive and negative, when you square it, it becomes positive. Therefore, when you are taking the square root, you have to consider both plus or minus. And when the function is decreasing, that is where the minus part is incorporated with. When the function is increasing, that is where the positive square root part is incorporated with. So you put the negative sign only because this function is decreasing. Okay, because this is the place where the function is decreasing, and therefore the negative square root, that is why we put the negative sign. Okay, because the function is decreasing, so your inverse function becomes the negative, right? Okay. So that's done for the decreasing part, right? Now let's look at the increasing part. That's the second case when x is in between 0 up to 2. That is where the function is increasing. Now there you consider your inverse function positive square root. Okay, so this is the inverse function of y. Now you consider only the positive y because the function is increasing now. Okay. And if you find fyy now, well, it is same thing, only the sign is the difference. So we'll do that quickly, since the calculations are already done with the negative part. So you'll end up with the same thing, 1/3 d/dy now, positive square root of y. So this will give you right. Again, it is 1/6 square root of y. Okay. Now, what is the limit of y? Y is x square. So y will be from 0 to 4. Okay. So you have to be careful now, right? Within 0 to 1, y is, okay, you have a certain answer within the interval 0 to 1. And again, from 0 to 4, again, you have 1/6 square root of y. So y has overlap. 0 to 1 is also included in the first case. 0 to 1 also included in the second case. Although it is from 0 to 4, 0 to 1, it's an overlap. Okay, so you have to be very careful with how you write the answer. Okay. Right, so I'll draw it. This is for y, okay? 2, 3, 4, up to 4. From the first case, you found that 0 to 4, you have 1/6. 1/6 square root of y. And from the first case, you found within the interval 0 to 1 also you have this one, right? Now, how do you incorporate these two? And how do you write the final answer? Think about it. They have to write the final answer in this format, right? There is an overlap in the support. So how do you tackle that? Yes, what do you think? So this is the overlap. Okay, so this is how we do it. 0 to 1, you have 1/6 square root of y from case 1 and another 1/6 square root of y from case 2. Now, when you have this probability 1/6 square root of y, that is the probability within the interval 0 to 4. All the values within this given interval, they will have the probability 1/6 square root of y. That means in the interval 0 to 1, from the second case also you have 1/6 square root of y. Within the interval 1 to 2 also you have that, 2 to 3 also you have that, 3 to 4 also you have that. Okay, so therefore, I'll split this into 2 like this. Okay, 0 to 1 and 1 to 4. Remember, this is the probability that you have in all the intervals, right? Depending on the value of y, the probability will change, but this is the function. Now, what do you see? Within the interval 0 to 1, you have 1/6 square root of y 2 times. So that means you have to add these together, right? Because from 0 to 1 interval, you have the probability coming from case 1 and also from case 2, right? If you go back to this one, this probability and this probability, right? You have to add them together, right? Within the interval, you have a probability part coming from case 1 and also from case 2. So that means this 1/6 square root of y should be added to this 1/6 square root of y coming from the second case. Therefore, within the interval 0 to 1 for y, you have 1/6 square root of y 2 times. So what does that mean? That is 1 over 3 square root of y. And then in the interval 1 to 4, you have 1 square root of y. And all the other places it is 0. So this is how you have to write the final answer. Okay, is this clear? Why we add these two components together and then split the interval, the overlapping part separately and the rest. Okay, so 0 to 1 is the overlapping part. So you can combine these probabilities together, and then 1 to 4, the other overlapping part. The non-overlapping part. Okay, so here will be the final answer. Is this clear to all of you? So this is how you do when you have a function which is, increasing, decreasing, both of them, the patterns are there. You split the function into increasing part separately, decreasing part separately, and then calculate it, right? So if you think about the triangular functions, that is also how you have to do it. Okay, say for example, if you have a function like this. Okay, this part is increasing, this part is decreasing. So you find the intervals separately and find the answer. And now in this case, see, you have the overlap. So you have to add them together, A to B, B to C, and add them together, the two probabilities, and whatever the interval for y, that will be your answer, right? They have to consider the two behaviors separately and then combine it like this. Okay. Any questions so far before we move on to the next section? Okay, then shall we move on to the next section? Now we are going to the bivariate case. So we looked at both continuous and discrete univariate case, how to apply the transformation method. Now we are moving on to the bivariate situation. Okay. We'll start with the discrete and later we'll move on to the continuous case. Right. So here's the definition. This is going to be a little bit lengthy definition, but the outcome is very simple. So we have x1 and x2, two discrete random variables with the joint PMF. Let's write the joint PMF. x1, x2. These are capital X1 and X2. And you have simple X1 and X2. Right, here's the joint PMF of X1 and X2. And let's say we are going to define Y1, which is the function H1, a function of both X1 and X2. And we are going to define the second function. Now this is bivariate case. So you have two. Y2, that is a H2 function, again a function of X1 and X2. So function H1 and H2, they are two different functions, maybe the same, but anyway, H1 and H2 are functions of both X1 and X2, bivariate. Okay. And we are going to define one-to-one transformation between the points X1, X2 and Y1 and Y2. Let's show that the equation Y1, okay. The equation Y1, what is the equation Y1? H1, X1, X2. And what is Y2? H2, X1, X2. they can be solved uniquely for x1 and x2 in terms of y1 and y2. That's okay. So that means if you have y1 equals a function of x1 and x2, y2 equals another function of x1 and x2, but they can be solved and write x1 in terms of y1 and y2 and x2 again in the terms of y1 and y2. That means they are the corresponding inverse functions. Okay. So what are these solutions? That x1 will be h1 inverse y1 and y2. So you write x1 in terms of y1 and y2 and x2 again in terms of y1 and y2 like this. Okay. Then the joint PMF of y1 and y2, that is what we want. That will be finally simply you take the joint density of x1 and x2 and replace x1 with what? H inverse, h1 inverse y1, y2. That is x1, and x2 will be replaced with h2 inverse y1, y2. Right? So all these explanations at the end, what will happen is you take the joint density of x1 and x2 and replace x1 with, the inverse of y1 and y2, and x2 with again the inverse of y1 and y2 corresponding on the functions x1 and x2. That's it. Right? Okay. Here's an example. I use another page because it's going to be a little bit longer. I'm going to use another page. Okay. So here's the example. Now remember, we are in the discrete case. Okay. So I'm going to use Poisson distributions. Our x1 is Poisson with the parameter lambda 1. And x2 is another Poisson with the distribution with the parameter lambda 2. And they are independent. So that's something nice. Okay, x1, x2 are independent. You want to find the joint distribution of y1. What is y1? x1 plus x2. Okay, you want to find the density of y1, which is x1 plus x2, and y2, which is x2. So you want to find the joint density of y1 and y2. What is y1? The sum of x1 and x2. y2 is simply x2 itself. Okay. Now remember, we did the distribution function method for summation. That is for the continuous case. Okay, that method cannot be applied for discrete situations, right? So now let's see how to use the transformation method in order to find the sum of two discrete random variables. Okay. Now in this case, we are going to use the transformation method. Okay. So let's go back to the function. Both of them are Poisson. They have different parameters, lambda 1 and lambda 2, and it's given that they are independent. Our target is to find the joint density of y1 and y2. The joint density of y1 and y2, where y1 is the sum of x1 and x2, y2 is x2 itself. Right? Now, if you go back to the definition, what do we need? We need the joint density of x1 and x2 first. The joint density of x1 and x2. That means we need the marginals of x1 and x2, and if you multiply them, you get the joint. Why? Because x1 and x2 are independent. Can you remember? When the random variables are independent, the joint density function is the product of the marginal densities, right? So when you have Poisson distributions x1 and x2, if you know the marginal density of x1 and x2, you can easily write it because it's given, it is Poisson. You can multiply the marginal densities and get the joint density. And in that joint density, wherever you see x1 and x2, you replace them with the inverse of these corresponding functions. Very simple. Okay. So what is the first step? First step is to find the joint density of, if it is given, you can use it. But in this case, it is not given. Okay. To find the joint density of original x1 and x2. Find the joint density of x1 and x2. That is the first thing you have to do because it is not given. And we know that x1 is independent from x2. Therefore, if you can find the marginal densities and multiply them together, that will be the joint density of x1 and x2. So this is what we want. So shall we write the marginal densities? What do we know? X is Poisson. Poisson with lambda 1. So that means what is the PMF? Can you remember the Poisson distribution? Can you remember the Poisson distribution? This is the Poisson density. Now in examinations, we usually provide the density functions in a table as supplementary, okay? So you don't have to memorize them, but eventually you will memorize them, okay? So here's the Poisson density. Always the x1 values will be 0, 1 up to infinity, right? And x2 is also Poisson with lambda 2. So you can write the marginal density of x2, that will be e to the negative lambda 2 to power the variable x2 divided by x2 factorial. x2 will contain values 0, 1 up to infinity. Okay. Since they are independent, multiply the marginal densities to get x1 and the joint density of x1 and x2. Can you do that? You multiply these two together, right? So what do you get? When you multiply e to the power exponents, you can add them. So let's write it together, lambda 1 plus lambda 2, the negative sign outside. So you add negative lambda 1 and negative lambda 2, and lambda 1 to power x1 times this one, lambda 2 to power x2. At the bottom, you have x1 factorial times x2 factorial. So that is the joint density of x1 and x2. Both of them have values 0 up to infinity. So the first part is done. What is the first part? Find in the joint density of x1 and x2. Some questions it will be given. Okay, if it is given, you can proceed with that, finding the inverse functions and applying the formula. But if it is not given, there should be information how you can derive it. In this case, it is given that they are independent. So we know the density functions, multiply them and get the joint density. Okay. Now we have the joint density. Now next is to find the inverse functions, right? Second step, you have to find inverse functions. That means you have to write x1 in terms of y1 and y2 only, and x2 in terms of y1 and y2 only. Then wherever you see x1, x2, you have to replace them with corresponding inverse functions of y1 and y2. Right? Can you do that? Let's write down these two functions. Y2 equals x2. Now using this information, find what is x1 and find what is x2 only in terms of y1 and y2. So I'll give you some time to derive them. So anybody who got the value of x1 and x2, x2 it is obvious, simply y2. What is x1? How do you find it? x1 will be y1 minus x2, but x2 is y2. So you can write this as y1 minus y2. Okay. Is this clear? So what is this? This is our inverse function of h1. And this is our inverse function of h2. So the inverse function of h2, you have only y2, right? And inverse function of h1, it is y1 minus y2. Is this okay to all of you? How to find x1 and x2 in terms of y1 and y2 only, right? Now we move on to the last step. What is the last step? You can apply it to the formula. What is our formula? Py1, y2. This is what we want. This will be to get the joint density of x1 and x2, and wherever you see x1, you replace it with the inverse function of h1. We have it. And wherever you see x2, you replace it with the inverse function of h2. That's it. Right? Shall we do that? So what is our P1, X1, X2? Here's our X1, X2, right? So let's write it again here. So it will be easy for you to grab it. Right? So what are we going to do now? Instead of X1, you have to replace it with Y1 minus Y2. And instead of X2, you have to replace it with Y2. So shall we do that? E to the negative lambda 1 plus lambda 2 as it is. Lambda 1 to power X1. What is X1? Y1 minus Y2. And lambda 2 to power x2. What is our x2? y2. At the bottom you have x1 is y1 minus y2 whole thing factorial times x2 factorial is y2 factorial. Okay. So this is how we write the this is your final answer of joint density of y1 and y2. And when you know the joint densities, you can even find the marginal densities of y1 and y2 also. Now, that's not the end. Why? You have to find the support. Okay, so that is the next step. Let's try to find the support. Okay. So we know that x1 is greater than or equal to 0. x1 is 1, 0, 1, 2 up to infinity. Okay, so x1 is what? x1 is y1 minus y2. So that means y1 minus y2 will be greater than or equal to 0. So which means y1 is greater than or equal to y2. Or in the other way, y2 will be less than or equal to y1. So that means y1 and y2 are not independent. Although x1 and x2 are independent, y1 and y2 are not independent. Right? Okay. x2 is greater than or equal to 0, which means x2 is y2, y2 is greater than or equal to 0. Right? So how do you write the final answer? So you can fix one, either y1 or y2. Okay. So let's fix y1. So how do you write the support of y1? y1 is where do we start? Okay, if we let's fix since we have y1 greater than or equal to, okay, let's say you can do it either fixing y1 or y2. Okay, so I'm going to fix y1 If you think y1 is going from 1, 0, 1, 2 up to infinity, where will y2 go? y2 should be less than or equal to y1, but it is greater than 0. See, y2 is less than or equal to y1, but it is also greater than 0. So it should go from 0, 1, 2 up to where? But it should stop at y1. See, y2 is less than y1. So whatever the value you have for y1, y2 should stop at there. If y1 is only 0, y2 will be also 0. If y1 goes up to 0 up to 5, y2 will go also from 0 up to whatever y1, okay, the limit of y1. Okay, so that is how you find the support of y1 and y2. You can write this with semicolon here. Right? This support, you can write it with a semicolon here. Okay, this is the easiest way because we start with 0, right? Fixing y1 and writing the limit of y2. So you can clearly see that y2 is depending on y1. So they are not independent. Although x1 and x2 are independent, y1 and y2 are not independent. Right. Is this okay? Is this clear how you got the support? Right. So from this, I'll give you some extra things that will be very useful to you. If you have Poisson distributions, okay. If you have independent Poisson distributions, xi having the same lambda, same parameter lambda, and if you find the sum of xi's for any, say I goes from 1 to n, that means x1 plus, x2 plus up to xn. So y is the sum of x1 up to xn. And if x1 and if all these xi's are independent and they have the same parameter lambda, we can show that y will also have a Poisson distribution. Excuse me. And the parameter will be the sum of these parameters. So lambda plus lambda, how many times? N times. Which means it will be Poisson n times lambda. Okay, so this is something nice and you can even prove it. And there are many other cases like that. You can easily combine the summations when they have the same rate and independent. Okay. Right, so let's do another example next time. Right. So we'll finish the lesson for today with that example. Do you have any questions so far? I have uploaded the second tutorial. Right. Try to do it. Last questions, you may not be able to do it yet because it contains what we are going to learn in the next lesson. But the first few questions you can try. So try them. You don't have to submit it, as you all know. Keep the answers with you. We'll do a discussion after we finish chapter 3. Okay, so meanwhile, try to do the questions that are possible, right? And keep the answers with you. Okay, no questions? So I will upload these notes and also the video to your Google Classroom so you can refer it later.